So this is a video for geometry. It is chapter 4, section 4, and it is proving triangles are congruent using two methods, side, 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 and side, angle, side congruence. So first we're going to start off with side, 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 and of course the acronym SSS stands for side, side, side congruence. And here is our postulate, and it is a postulate, so it's assumed to be true. We don't have to prove the theorem. And it states, if three sides of one triangle are congruent to three sides of a second triangle, then the triangles are congruent. Now let me just tell you why these two theorems, and of course there's two more coming after it in the next section, are extremely helpful to us. You might recall in our previous lesson that in order for us to be able to prove that two triangles were congruent, we had to come up with 6 different pieces of information. We had to determine that 3 pairs of sides were congruent, and also that 3 pairs of angles were congruent, and totaling 6 items before we could prove that the triangles were congruent. Well, in this case, we basically just cut our work in half. Instead of having to find 3 pairs of sides and 3 pairs of angles, we only have to find 3 pairs of sides. If we can do that, then the two triangles are congruent. So basically what we're saying here is that if AB is congruent to DE, as it's marked, BC congruent to EF, and AC congruent to DF, then triangle ABC will be congruent to triangle DEF. Now the bad news is that, of course, the section is called Proving Triangles Congruent, so we do have to do some proofs, but hopefully they won't be too hard proofs. So here we go with our first example. It says write a 2-column proof, and it is given that GH is congruent to KJ, so I've gone ahead and marked my diagram, GH congruent to KJ, and also we know that HL is congruent to JL. So I've marked those two, and I've already put them into my proof. And then it says in the second part of the given statement that L is the midpoint of GK. So here's L, and it's the midpoint of GK. Because it's the midpoint, that means that this point L is going to cut the segment GK into 2 equal parts. So that means that GL will be congruent to KL. So in my proof, we're going to say that GL is congruent to KL, and that's by definition of midpoint or the midpoint theorem. So I'll put here midpoint theorem. We had that theorem a few chapters back, a couple chapters back. So 3 is GL is congruent to KL by the midpoint theorem. So now we have all 3 pairs of sides congruent. We have the first pair here, second pair there, and now with the help of the second given statement, we can say that the third pair of sides is congruent. So now that we've done all 3 pairs of sides, then all that's left to do is say that triangle GHL is congruent to triangle KJL. And the reason for that is side, side, side. And then you put your Helmholtz, and you call this problem done. All right, so I hope that like I stated earlier, that that proof wasn't too difficult, and hopefully most of the proofs will be pretty straightforward like that. Okay, so now I want you to try this one. It gives you that triangle QRS, this big triangle here, is isosceles with QR congruent to SR, so there's 1 pair of your sides. It also tells you that RT, this right here, bisects QS, so that means that it's going to get you 2 equal parts here. And then you got to come up with 1 more side, and then you can prove this guy as well. So in example 2, we have a little bit more of work to do here, but they want us to use coordinate geometry in this case, which requires a distance formula as well. So let's just go through what it says. This triangle ABC has vertices 1, 1, 0, 3, and 2, 5. Triangle EFG has vertices 1, -1, 2, -5, and 4, -4. So first part they want us to do is graph both triangles on the same coordinate plane. So that's the easy part. So we're going to go 1, 1. So here is 1, 1 for point A. 0, 3, so x is 0, y is 3, 1, 2, 3, there's another point right there. And then 2, 5, so here's 2, and then 5 is way over here. So I'm supposed to make a triangle out of this little guy. like so. So there's my first triangle. And then that's ABC. So that would be 1, 1 was right here, A. 0 through over here, B and C. Okay, then we have EFG has versus 1, -1. So here's 1, -1. And then we have 2, -5. So here's 2 and -5. And then we have 4, -4. 1, 2, 3, 4. And -4 is over here. So somewhere right about there. And now we've graphed both triangles on the same set of coordinate axes. So that's part A. 1 negative, this is E, this is G, and this was F. Okay, so now in part, because use your graph to make a conjecture as to whether the triangles are congruent. Now, just by looking at the triangles, you can probably tell that they're not congruent. So my conjecture is going to be that the sides are not the same, so the triangles are not congruent. That's my conjecture. But that isn't enough for them. In part C, it says write a logical argument using coordinate geometry to support the conjecture you made in part B. So basically, they want me to prove it, but I'm not going to prove it with a true column proof. I'm going to prove it with a distance formula. So what I'm going to do is I'm going to make sure that the vertices are in the right order. Remember we talked about this earlier. And like you might be thinking, well, how do I know which side compares to which side? Well, we know already that we have ABC. We're trying to see if triangle ABC is congruent to triangle EFG. All right, so that's the question. But if it's the case, then AB has to correspond with EF, and BC corresponds with FG, and AC corresponds with EG because they have to be in the right order, right? So what we have to do, sadly, is do the distance formula 6 times to prove this. So we're going to go AB. We need to find BC and AC. So for AB, we have to do use point A and B. So we're going to do the distance formula, and I'll put it up here for you in case you don't remember it. It's the difference in the x value squared plus the difference in the y values squared. Okay, so we're going to go with AB first, points A and B, and the difference in the x values, I'm going to go 0 minus 1, which is -1 squared, and the difference in the y value is going to be 3 minus 1, which is 2. So -1 squared is 1, and 2 squared is 4, so 4 plus 1 is 5, so we're going to get root 5. Okay, for BC, I'm going to use these 2 points, and again, I'm going to go, the difference in the x values is 2 minus 0, which is 2 squared. And the difference in the y values is 5 minus 3, which is also 2, so another 2 squared. And 2 squared is 4, and 2 squared is 4, and 4 plus 4 is 8, so you get the square root of 8, which is the same thing as 2 root 2. So for BC, that's of course if you remember how to simplify radicals. You can leave it as a square root if you'd like, but it is 2 root 2. And then AC, so now we're going to go from A to C. The difference in the x values is 2 minus 1, which is 1 squared. And the difference in the the y values is 5 minus 1, which is 4. 1 squared is 1, 4 squared is 16, so you get 17. So this triangle is scalene, none of the sides are the same. And now what we're going to try to find out is if the second triangle has any of these same lengths, and then it would be congruent. So to do that, we have to go with EF. We need to find FG. And we need to find EG. Okay, so EF, do the same thing we did with A, B, and C. With EF, we're going to use point E and F, and the difference between the x values is 2 minus 1, so that's going to be 1. The difference in the y values is -5 minus a -1, so that's -5 plus 1, and -5 plus 1 is -4. So 1 squared is 1, negative 4 squared is 16, so you get square root 17. So those two seem to be the same. FG is going to be difference in the x's. 4 minus 2 is 2. Difference in the y's is negative 4 minus negative 5. Remember, negative 4. So minus and negative is a positive, so negative 4 plus 5, which is 1. So 2 squared is 4, and 1, so you get 5. And then, so those two lengths appear to be congruent. And then EG is going to be the difference in your x coordinates. 4 minus 1 is 3 squared. And the difference in your your y's, negative 4 minus negative 1 is negative 4 plus 1, which is negative 3 squared. So 3 squared is 9, negative 3 squared is 9, and you get the square root of 18. And that's where everything falls apart, because we had a square root of 8, not a square root of 18. All right, so based on that, we can actually now logically say that triangle ABC is not congruent to triangle EFG, because you can't prove side-side-side congruence. So that is how you do example 2. And now you're going to want to do the exact, I didn't want to rewrite all of the steps again, but you're going to do the same thing, A, B, and C, parts A, B, and C, but for these two triangles, J, K, L, and NPQ with these vertices. So you want to graph them, you want to make a conjecture, and then you want to logically prove that with your coordinate geometry. All right, so that would be example 2. And now we're going to go to the other theorem that is similar to side, not exactly, and that is side, angle, side. Now, side, angle, side, those letters are not just there because they want to look pretty. The positioning of the letters actually matters. So the theorem here, or the postulate here, sorry, this is also a postulate, so it's assumed true, we don't have to prove it, is that if two sides and the included angle, so I put here in parentheses a way that you could understand what included means. Included means that it's included in the two sides, so it's in between the two sides. So for example, we have AB here marked congruent, and we have BC marked congruent, and so when you put those two sides together, they make this angle, and that's the angle that's in between the two sides. There's another angle over here, but this angle is not in between these two sides, and this angle is not in between these two sides. So it has to be the angle that is in between the two congruent sides. If that happens, so if two sides and the included angle of one triangle is congruent to two sides and the included angle of a second triangle, like this one, then the two triangles will be congruent. So basically, a breakdown over here is if AB is congruent to DE, and in turn angle B is congruent to angle E, and side BC is congruent to side EF, then the triangles are congruent. But again, the really important thing is that the A is in between the two S's, to remind you that the angle has to be in between the two congruent sides. Obviously, all angles are between two sides, but it needs to be the angle that is in between the two congruent sides. All right, so, and again, we have a lovely proof here. And so, okay, so we're going to write a two-column proof again like before. It's kind of already got started for us. So it says here, given the WX is congruent to YZ, so here's WX, it's congruent to YZ. I've put that in my proof already. And then we're told that WX is parallel to ZY, and that's also given. Now you got to wonder, why are they telling me that WX is parallel to YZ? We talked about this in class before. They don't just give you information randomly. You need to understand, why are they telling me that something's parallel? When you know that something is parallel, it's very important that you start looking for those relationships among angles and parallel lines, like alternate interior angles, corresponding angles, consecutive interior angles, and all those ones that we learned a while back. So when I do that, I realize that I do in fact have alternate interior angles right here. So because I can't call this angle angle X because there's too many angles in this vertex, I have to use 3 letters. So I'm going to go with angle WXZ is congruent, and if I go WXZ, you'll notice that I'm going from the congruent side to the non-labeled side. So to get this angle, I have to go from the congruent side to the non-labeled side. So I'm going to go y, z, x are congruent because they are alternate interior angles. Okay? So now we've got one pair of sides and we've got one pair of angles and we need one more pair of sides. And it has to be the side that is going to like sandwich the angle. So if you're thinking to yourself that it's going to be WZ, it can't be WZ because then the angle would have to be over here. The angle, the side that we're looking for has to be XZ. And lucky for us that XZ, we have what we call a shared side. I mentioned that again in the previous class. Both of these triangles are sharing this side. So when they share a side, we can put an X there to mark that they are congruent, it is congruent to itself. So in step 4, we're going to say that XZ is congruent to XZ. It's congruent to itself, and that is for the reflexive property. Reflexive property congruence, yay. And now we have two pairs of sides, one pair of angles, and the angle is in between the two congruent sides, and therefore we can prove that triangle WXZ is congruent to triangle YZX by side, angle, side. Helmos? And we are done with our proof for example 3. Now, isn't that lovely? And then we have, I think, one more. So there's the do-it-yourself number 3 for you. And then we have one more example. And in this example, we're going to use side, angle, side, or side, 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 depending, to get our proof. But the difference between this proof and the ones that we've been doing is that the end of each of the other proofs that we did today had proved triangle blah is congruent to triangle blah. When you know that two triangles are congruent to each other, you know you're going to use side, angle, side, or side, side, side. But in this case, it's not telling us that triangle CFD is congruent to triangle CEB. It's an angle. An angle is not a triangle. So we're going to use what we learned in our previous lesson, which is CPCTC. That's an acronym, but it stands for corresponding parts of congruent triangles are congruent. So we already learned in the previous lesson that if two triangles are congruent, then it means that all of their parts are congruent. So we're going to use that. So I'm just going to tell you, this is going to be a little bit of a longer proof. It's going to be a little bit complicated, so kind of try to pay attention. But I'm going to tell you right now what we're going to do. The first thing we're going to do is we're going to prove that these two triangles are congruent. The two triangles that are on the right and left, because obviously there's 1, 2, 3 small triangles, and then there's even the big triangles, that's 4. And then if you can even imagine it, there's 2 more triangles if you kind of trace B to C to E, this triangle here, and it's overlapping FDC. So that's another 2 triangles that you've got. So now you've got 5 different triangles. 1, 2, 3, 4, 5, and then the original 6. So there are 6 triangles happening here. So it's going to be kind of crazy. But let me just tell you, a little plan. Our plan right now is to prove that these 2 triangles are congruent. And then if these 2 triangles are congruent, then these angles are congruent. And if these angles are congruent, these angles are both linear pairs with these angles, okay? And then these angles are going to be parts of the big 2 triangles that we've got going on here, all right? And eventually, if you can see here, it says prove CFD. And if you think here, CFD is this angle right here. And I probably want to put that in a different color because we haven't proved it yet. But there's CFD is congruent to CEB, and CEB is this angle here. Okay? So if you think about this big triangle that I'm tracing in blue, then CEB is an angle of the big blue triangle. And then if I can be so bold here and trace out this triangle in pink, then you can see that this angle over here, which is CFD, which is the angle they're talking about here, is the angle that they're discussing. So you can see how there are corresponding parts there. But anywho, so again, our plan right now is to first and foremost, if you're already scared, first and foremost, let's just take a step back. And the first thing we have to do is prove that these two smaller triangles are congruent. So let's do that first, and then we'll worry about everything else later. Okay, so we already know that BC is congruent to DC because it was given, and also that FC was congruent to EC because that also was given. So we already have two pairs of sides. In step 2, they told us also that angle BCF, which is this little angle here, was congruent to DCE. So really the only thing that's left for us to do is to actually state that triangle BCF is congruent to triangle DCE. Okay, because you already have side, angle, side. You have the angle in between the two sides. So that's going to be our step 3, side, angle, side. Now, as I said earlier, because the two triangles are congruent, then all of their parts are congruent. So even though angle BFC was not part of the original process of proving the triangle is congruent, angle BFC is in fact congruent to DEC. Okay? And that's because of corresponding parts of congruent triangles are congruent. So CPC2C, it's an acronym. Okay, so now we know that this angle right here is congruent to that angle right there. Okay, our next part is to say that, I'm not sure how we want to say that, but basically that the angles, let's see here, BFC and angle DFC are line pair. Also, we know that angle DEC and angle BE or CEB, are also a linear pair. Okay, so I'm going to get out of the way so you can see what I just did. Basically, I'm saying BFC, so here's BFC, this angle right here, and DFC are a linear pair because they form a line. Okay, but also we know that DEC on the other side is a linear pair with CEB as well. So that's definition of linear pair. Definition of linear pair. And because they're a linear pair, we're going to say angle BFC and angle DFC are supplementary, and so are angle DEC and angle CEB, also supplementary. 6 here, and that's because of the definition of linear pair again, or you can put the supplementary theorem, supplements theorem. Okay, so we know that because they're a linear pair, they have to add up to 180. Okay, and then finally, I know this seems a little tedious, but finally, because you have two different angles that are supplementary to congruent angles, then we can finally say in step 7 that angle CFD is congruent to angle CEB, which is what they wanted us to prove in the first place. And the reason is for the congruent supplements theorem. And the congruent supplements theorem was a theorem that we had back in the previous chapter that stated that if you have two different angles that are supplementary to the same or congruent angles, then then the two angles are congruent, and that's what we have. We have two separate angles, these two separate angles that are in blue, that are supplementary to the same, well, not in this case, not the same angle, but they're congruent angles. So because of that, that makes the blue angles congruent as well. So don't forget your Helmos. And trust me, the proof that you have to do is not going to be as complicated as this one, but it is going to require you to use CPCTC. So you're going to want to prove, in the do-it-yourself question, you're going to want to prove the two triangles are congruent first. And then after you've proven that the triangles are congruent, you can prove the parts are congruent by using CPCTC. So once you have done that, you will have completed your notes for this lesson, and I will see you in class, and thank you for watching.